All right, so we're in the chapter on free convection. A lot of times they'll call it natural convection. What drives it? Well, we're going to talk about that right away. It's a long chapter, but we only have 2 lectures in it. Okay, so let's jump into it. What drives natural convection? You have to have 3 ingredients. You have to have gravity. You have to have a body force. Well, gravity is not the only body force you can have. You can have a rotating system, and then it would act like a body force, a centrifugal force. But the gravity is predominant body force that gives us natural convection. If you're working for NASA and you need to put something up where there's 0 G, are you going to have to consider natural convection? Not really. Not gravity driven. Here you go. You have to have a density as a function of temperature. So the density changes with temperature, and temperature is a function of position. Those 3 things give us natural convection, meaning there will be fluid motion without a pump or a fan or anything to make it move. It'll naturally just move. Hot air will rise, that's the typical saying, and cold air will sink. And that will promote heat transfer. We start with a simple analysis. We want to take a look at the velocity profile as well as a temperature profile for a particular case. And the particular case is we have a knife-edged plate pointing downward, so it's a vertical plate, not a horizontal. And it's in a large quiescent fluid, meaning there's nothing to force the fluid to flow over that plate. It's in a large, naturally wanting to just be stationary fluid. But the plate is hot. And if this is in the presence of gravity, the fluid adjacent to the surface of the plate will be warmer than the fluid further away. Hence, you got hot air trying to rise, cold air sinking. And so this is the knife edge. You can just continue this top edge off into infinity. And they put a coordinate system at the bottom of the knife edge and only look at one side, the right-hand side of that knife edge vertical hot surface in a large pool of quiescent fluid. And we introduce y going out and x going up. This is very common. You'd think that's kind of backwards. Shouldn't y go up and x out? Sure, but we're going to do y is going perpendicular out from the hot surface. And what do we get growing right here? We get growing a velocity profile like this. So at some distance up, you can talk about the thickness of that boundary layer. The boundary layer caused by the fluid sweeping up over that hot plate. The velocity profile, well, what does the velocity profile look like? Way out here, it's kind of U infinity. What is U infinity in a quiescent fluid? 0. It's really not moving. What is the velocity at the surface of the vertical plate that's not moving? 0. But inside, we have a very unique type of velocity profile. It goes up. It does something like that. And so our velocity is more complicated than in the forced convection over a knife-edged plate, isn't it? So we're interested in U as a function of either x or y. What is it? X or y? U is a function of which one? U is the velocity in the x direction as a function of y. U is a function of y. And now, what about temperature? You can plot it on the same plot, or you can redo, put the vertical plate here again, put the same coordinate system, y and x, talk about the growth of a thermal boundary layer, then come up at a particular location, let's say at this location right here, we're interested in delta T, the thermal boundary layer thickness, and we want to sketch the thermal profile. Well, we'll do this, we'll put 0 and kind of put up a local temperature profile here. Way out here, it'll be T infinity. I'm going to show it above 0. And up here at the surface, we'll put TS. And so it does some temperature profile like that in the boundary layer. Make sense? Maybe I shouldn't have it so flat right there. Maybe I should have it like this, something like that. Okay. So what are we looking for here? T as a function of y. Well, what equations are we going to use? We're going to use the continuity. We're going to use the x momentum, the y momentum, and the energy equation, or the heat equation. Those four equations can be used to solve for the temperature everywhere in our domain and the velocity everywhere in our domain. Well, the continuity, we're going to assume it's steady state. Let's not take a look at that. Let's focus in on the x momentum equation. We have rho times u, partial of u with respect to x, plus v, partial of u with respect to y. What does all that represent? Keywords. I'm looking just for keywords. What does that represent? Advection of momentum. Flow, sweeping. So it's advection of momentum. Equal to, and then you have two things that can change it, as well as the very last term, mu, second derivative of u with respect to y squared. What is that last term? Diffusion of momentum because of viscosity in the fluid. Faster fluid adjacent to slower fluid will try to change the momentum by dragging that slower fluid along, speeding it up. Well, we're going to have a body force term minus rho g, meaning here I have g and it's in the negative x direction. And rho times g, isn't that our body force term in our momentum? But there's one other term, and it's the rate of change of pressure with respect to x, and we'll put a minus sign on that. That's our x momentum equation. If there's a pressure pushing it, a pressure difference. Okay. Well, we go to the y momentum equation. This is outlined in the book, and I'm kind of going fast. But if we go to the y momentum equation, it just boils down to that the rate of change of pressure with respect to y is equal to 0, which means that the pressure is only a function of x. And then we think about it, we go far out into the fluid, so go out into the far away from the boundary layer, far away from the hot plate. If the pressure is only a function of x, then what we find is that the change in the pressure with respect to x is really the change in the pressure far away with respect to x, and it's just minus rho infinity g. It's hydrostatic pressure far away. It's like a column of fluid far away, and we just have hydrostatic pressure. And the pressure way out there just penetrates into the boundary layer. It's a long discussion. Maybe I'll let you think about it some more. But we can put this in here. And when we do that, we still get the advection term equal to, and what do we pick up? We pick up rho infinity minus rho times g plus the viscosity term. So these two terms combine to this term. Now you can see it starting to take shape. Oh, if the rho is lower inside the boundary layer where it's warmer, then I'm going to get a forcing term to drive the convection. Right? We introduce a parameter called beta. I'm going to talk about more about it, but it's on the next page. But it's the volumetric expansion coefficient, volumetric expansion coefficient. It's defined as minus 1 over rho, the rate of change of rho with respect to temperature holding pressure constant. It's how does the fluid expand as temperature changes. So I'm going to go to the next page and explore this new parameter known as the volumetric thermal expansion coefficient beta. It's minus 1 over rho, the rate of change of rho with respect to temperature. So I'll do a little changing here. This is, I can take this partial derivative and approximate it by a difference. So it'll be how does rho change over the temperature, true? Well, we'll start at rho infinity and T infinity, and we'll move to a new rho and a new temperature. So this is my approximation to that derivative at constant pressure. Constant pressure. Minus 1 over rho, 1 over rho. All right, so that's what beta is approximately equal to. I approximated that derivative. So I see that this rho infinity minus rho divided by rho is equal to, that minus sign goes in, flips it, I pick up a beta T minus T infinity. Make sense? So if I'm interested in saying, how does the density change? Well, this is like a normalized density change. It's equal to beta temperature change. So let's go back to this previous slide. And we had a rho over here, and we just divide all the terms by rho, by rho, by rho. We see that, oh, we can replace that by G beta T minus T infinity. This becomes a new second derivative of u with respect to y squared. And this is just cancels that rho on that advective term, u partial u with respect to x plus v partial u with respect to y. So it's almost like magic. It's like, how did we pick up this g beta delta t term? That's the term that drives the natural convection flow. True? How do we pick that up? Well, it's a few steps, and we introduce that parameter beta. All right. Let's talk a little bit more about beta. If I said I have an ideal gas, what's a good ideal gas? Air. We breathe it all the time. We treat it as an ideal gas. It behaves like an ideal gas. What do we know about an ideal gas? Is rho equal to P over RT? Is that the ideal gas equation? Sure is, right? So if I take this as the ideal gas equation, and then I take the derivative of rho with respect to temperature, holding pressure constant for an ideal gas, do I pick up P over R minus 1 over T squared? Yeah. And now what I'm going to do is we substitute into this equation. So the beta is equal to minus 1 over rho. So we're going to have P over RT for the 1 over rho times the partial of rho with respect to T holding. So it's negative P over RT squared. The minus signs, two of them turn into a plus. The pressures canceled, the R's cancel, one of the T's cancel, and we're left with a very simple, startling result that the volumetric thermal expansion coefficient for an ideal gas is equal to, very simply, 1 over T. Do you remember that? If you took thermo with me? I cover it when I cover thermo. I say, hey, we're going to see this in heat transfer if you haven't seen it already, so let me show it to you. Hopefully, maybe you recall if you took it with me. So this is a big result. So a lot of times you'll even see this has been replaced by 1 over T because you're interested in buoyancy and natural convection in air as an ideal gas. Let's ask some questions though. Ready for a clicker question? First clicker question. Liquid water can be treated as an ideal gas. True or false? All right, we'll stop it. And what about liquid water? Incompressible is a very good approximation for liquid water. It's not perfectly incompressible, but it's very much. How about an air, gas? Very compressible. Okay. Here's another question. For an ideal gas, at a temperature of 0 degrees C, the volumetric expansion coefficient beta equals plus infinity, negative infinity, 0, or some other answer. Professor, what was beta for an ideal gas? Beta is 1 over T. All right, we'll go ahead and stop. So somebody said, well, we derived that result knowing that we started with rho for an ideal gas is P divided by RT. This equation is the starting point, true? But tell me a little bit about this T and this P that students in Thermo 1 may make a mistake on, but you would never. Absolute, that's what we're looking for. Thank you very much. It needs to be an absolute pressure. Don't put in gauge pressure. And what about the temperature? Absolute Kelvin, not a relative degree C. While not at the times, they won't put in the exam, they won't put in 0 degrees C, they'll just put in 20 degrees C. They have to convert. Now, when it's 0 degrees C, it's pretty obvious. Ooh, I think I have a problem here, right? So the best answer is D, isn't it? It's some other value. It's the best answer is D. Hopefully I explained that well enough for you to understand. Let's try another one. Would you like to try another one? All right. For an ideal gas, beta is always greater than 0. All right, let's go ahead and stop it. Well, how can I put in a value of temperature in the beta 1 over T and get a negative quantity? Beta is always going to be greater than 0 for an ideal gas. For an ideal gas. True? All right. Somebody says, can we solve problems with other fluids like water? Let's say you said don't use 1 over T for water. Well, where am I going to get beta, Professor? Well, it's a property, just like a property like the specific volume. That's a property. Where would you get it? Out of a table. Just like the viscosity. Where do you get it? Out of a table. It's experimentally measured and then reported. Thermal conductivity. Where? Prandtl number. What's this last column? It's the expansion coefficient beta. It's multiplied by 10 to the 6 inverse Kelvin. So if I wanted to get it at, let's say, 300, I come over here, I grab that number that's 300 Kelvin. And so beta is equal to 6.1 times 10 to the minus 6, 1 over Kelvin. That's what beta is. For liquid water. For liquid water. All right. What do we remember about water? If you get it cold, 10 degrees, 6 degrees, 4 degrees, 2 degrees, get it down to 0 degrees. What does the density do as you're getting it colder, 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 colder? What is rho doing? Going up, it's more dense. But it does something very special. At what degree? What does it do? Hits a maximum. And then as it starts to get even colder, does it continue to get more dense? No, it actually starts to expand a little bit. All right, at 0, let's say we even drop it to -1 or something. Something's really dramatic going to happen as we go from LIQ to SOL. What's going to happen? It's going to solidify. It's going to turn to ice. Just another general question about your understanding of water and what happens when it freezes. Somebody wants you to continue this plot. Will it, at this point, as it turns to ice, go up dramatically, stay the same dramatically, or go down dramatically? Answer A, B, or C. What happens to the density as I go from liquid water, 0 degrees C, to solid water? Everybody in? It makes you think a little bit, doesn't it? All right. So what happens when you freeze it? Does it contract or does it expand? It expands on freezing. It takes more volume after it's frozen, meaning it's less dense. So what did the density do? Well, I didn't turn it off, did I? Doesn't it do that? True? Yeah. And so it'll go down. Dramatically, the density will go down. All right. Let's take a look at this. So what is beta again? Beta is the rate of change, 1 over density times the rate of change of density with respect to temperature. In this vicinity right here, if I heat it up, if I go from, let's say, 6 degrees C to 8 degrees C, what happens to the density? It goes down, doesn't it? And so the warmer fluid, let's say here, is at that density, and the cooler fluid at 6 degrees is at this density. What's going to happen to the more dense, cooler fluid? It's going to cool fluid in the presence of warmer fluid. The cool fluid's at 6 and the warm fluid's at 8. The cool fluid's going to sink. And the warm fluid is going to, I know 8 degrees C doesn't seem very warm, but relative to the 6 degrees C, it's the warm fluid, and it's going to rise. True? All right, let's try it over here. Let's talk about 1 degree C fluid. And let's talk about, I don't know, 2 degrees C fluid. There's not much space over there, right? So let's talk about 2 degrees C. Let's put 1 degree C as blue because it's colder, 1 degree C red because it's warmer. Is the warmer fluid, the 2 degrees C fluid in this case, is it more dense than the 1 degree C fluid?
Yes.
All right. So what's the more dense fluid going to do? The warmer fluid, W-A-R-M, I can spell, come on now. Warmer fluid will fall while the cooler fluid rises. Compare. Guess what? Isn't it the opposite? This is the vast majority of the time. That makes sense. Something warm, it's lighter, buoys up. Something cold, denser, sinks. But every now and then you can get it like, oops, hey, just opposites happening in this very narrow range. Yeah, it's pretty interesting, isn't it? So take a look over here. They tabulated. They put 10, 20, 30, 40. Talk about those values of beta. What's happening to those values of beta? They're going up. But what about this one at 4 degrees C? Something's interesting. What's the value of beta liquid water at 4 degrees C? 0. It's the slope. How does rho change with temperature holding pressure constant? 0. And what about this? Is beta positive or negative for liquid water between 0 and 4 degrees C? Negative. And the math will show you then that the warm fluid will sink in the presence of the cooler fluid will rise, will buoy up. That's more of an anomaly than to really be, beat in. But this brings up an interesting question, does it not? What are the units on this reported, where I grabbed out of Wikipedia or Engineering Toolbox? What are the units on beta? 1 over degree C. That reminds me, I need to ask a question. For liquid oil at 25 degrees C, the volumetric expansion coefficient beta is reported to be 0.00070 inverse degree C, 1 over degree C. I need the value of beta in inverse Kelvin. What is the value in inverse Kelvin? Oh, this is messed up. I know, I messed that up. Put it in Kelvin. These are all Kelvins. One of the answers is correct in inverse Kelvin. Everybody in? All right. So we'll go ahead and stop it. Sorry about the typo on that. That was giving me confusion. But what about, where does temperature show up? Well, these units on rho cancel with the units on rho. And so really the temperature shows up because it's the change of rho with the change in temperature. Isn't it the same numeric value? Now, a tougher question. I don't know why I ask these tough questions. Just, I don't know. Maybe I shouldn't ask it. Somebody says, same oil, same temperature, the volumetric expansion coefficient is the same. It's 1 over degree C. You already know, hey, if I want it 1 over Kelvin, I got it 1 over Kelvin. It's the same numeric value. But they said, nope, I don't need it 1 over Kelvin. I need it in 1 over Fahrenheit. 1 over Fahrenheit. This is a challenging question. One of the answers is correct. What is the volumetric expansion coefficient? All right, let's go ahead and stop it. So I know that there's probably not great syntax. I remember I always did not like the syntax for how they showed you an equation to convert temperatures. Do you remember that? They said, if you want the temperature, if you're given the temperature in degree C and you want to convert it to degree F, how did you do that in an equation? See, so Well, you'd multiply by 1.8, and then you would add 32. Is that the right equation? Somebody says, I don't like 1.8. It's 9/5. That's the same as 1.8. But I never liked it. But it's difficult to show this in an equation, how to convert temperatures. I don't know if you ever struggle with that. But it's kind of funny. It's like, hold it. T is here and T is here. I know, but that T is in degrees C and that T is in degrees F. And I just want to get them over. I want to convert it, right? So this is the type of way they write that equation. So let me try that same syntax and say something up here. I have beta is equal to the minus 1 over rho, the rate of change of rho, but I already have it in the rate of change in degree C. And I really need it in the rate of change of degree F. So I would just multiply by how much change in degree C per the change in degree F. True? And so this rate of change in degree C over change in degree F is either 9/5 or 5/9. Which one is it? The change in 5/9, isn't it? And so what is our best answer? B? Did you get it right?
Yes, I did.
I heard excitement. That's great. Hey, look at that, 50% of the class. This is super. So if we go back, this is the same thing. So it's sometimes the beta will be in these units, sometimes the beta will be in those units for oil. All right, now we have a good familiarity with what beta is. And then we have it in our governing equation, the volumetric expansion coefficient. Then what we do is we go back and we say, now I'd like to solve it. I'd like to solve it with this momentum equation, continuity equation, the energy equation. I'm going to transform it using dimensionless velocities, dimensionless temperatures, and then I'm going to pick up something that looks like this that drives the flow in the momentum, and Reynolds 1 over Reynolds Prandtl in the energy equation or heat equation. That looks very familiar. And then you say, well, the speed is proportional to, the speed squared is proportional to this term. Hence, you substitute for that term in the Reynolds number, and you pick up a new dimensionless ratio, and its name is called the Grashof number. We get a new number, it's called the Grashof number. It's analogous to the Reynolds number, but instead of forced flow pushing it, it's for natural convection. So this is what it looks like, and it's buoyancy over viscous, because what drives the flow for natural convection? Buoyancy forces. Buoyancy forces over viscous forces. It's kind of neat. You have the G, you have the beta, you have that temperature difference between the hot and the free stream or far away fluid. You have a L that's usually in the direction of the gravity acting on the surface or the body or the object. And you have nu squared. What is nu? Viscosity. Viscosity squared. Is this going to be dimensionless parameter? It'll be perfectly dimensionless, just like the Reynolds, just like the Nusselt number. So that's the Grashof number. Well, you then go and introduce stream function to satisfy continuity. You then introduce a similarity variable that I didn't come up with, some genius did, which is a function not only of y and x, but also Grashof. Then you have u works it out as a function, if I could just solve for f prime, where f comes into the x momentum equation, and this is our energy equation. There's just too much math, but I give you the Cliff Notes version, that somebody has sat down there, cast it into this very abstract form, numerically solved it, and reported the values. And this f prime right here is essentially velocity. You can think about this axis as being velocity profile. What is this eta axis? The distance y going out from the wall, from that vertical plate. And just look at a Prandtl number of 0.72. That would be this curve right here. That's like air, and that's like our velocity profile. It's peaks somewhere close to the wall, and it gradually goes out, and this would be around 5, the extent of the boundary layer. And the temperature profile, the same thing. Pick up on the Prandtl number of about 0.72, go like this, and it goes dramatically up to the wall. Far away, dimensionless temperature ratio goes to 0. Let's solve a problem. We have a thin 0.5 meter square plate, and we have multiple of them. So here they are, they come out like this, and there's another one like this, and another one like this. They're coming out on a conveyor belt that's being held up out of manufacturing, where they're initially at 54 degrees C, but they're cooled. They're vertically suspended, and they're vertically moving through, I don't know how you're going to do this, a large water bath that's 20 degrees C, and it's not being disturbed by the movement of the plates, so it's quiescent. The water is going to sit there far away from the plates and not move. What is the minimum spacing between the plates to prevent the interference between their free convection boundary layers? So what happens is you get a boundary layer growing up that way and a boundary layer on the other side growing that way. Maybe I'll take a look at it and look this way and this way. Here's my vertical plates, and here's the boundary layer growing, and here's the boundary layer growing, and they meet. They meet at when this is L equal to 0.15 meter right here for that height, and they meet right there. So the minimum spacing S between the two plates needs to be 2 delta the thickness at the end. So you say, well, what is the thickness, boundary layer thickness, after it goes from 0 up to L? What's the boundary layer thickness there? All right. So what we do is we calculate the film temperature of the, which is an average temperature, so I can get fluid properties for the water. So we get it at the temperature of the surface, the temperature of the water far away, we divide by 2. Temperature of the surface 54, far away 20, divide by 2, convert to Kelvin, and it comes in nicely at 310 Kelvin. We then can go and get from our table A6 properties like beta. It's 361.9 times 10 to the minus 6 inverse Kelvin. That's probably the hardest one for people to find, because you're used to already going into a table and getting the Prandtl number, 4.62, going and getting a thermal conductivity, 0.628 watts per meter degree C, going and getting viscosity, density, you can calculate the kinematic viscosity, etc. We get all our properties. Then we say, what I need to find is that thickness of the boundary layer when it's grown up by L of 0.15. So I look back here, and I'm saying, okay, I will call that about 5 right here. And so this, as you can see, eta is equal to 5, or 5 is equal to the thickness of the boundary layer, velocity boundary layer, divided by x to the Grashof as a function of x, divided by 4 to the 1/4 power. But we want to evaluate this at x equal to L. So 5 is equal to delta over L, the Grashof at L divided by 4 to the 1/4 power. So let me just grab this, edit, copy, come over here, edit, paste. So what we need to get is that the Grashof number at L. Well, what is the Grashof? G beta delta T to Ts minus T infinity, L cubed divided by nu squared. And we just got all our properties. We have everything to calculate the Grashof number. When we calculate it, it comes in at 7.37 times 10 to the 5. So we got the Grashof number. Then we can stick it in here. We know the L, and we find that the thickness at the top, after it's grown that far, the thickness is equal to about 0.00644 meters, which is 6.44 millimeters. And so the spacing is 2 times the thickness. That's the spacing S. And S comes in at about 13 millimeters. So it's making us go back and use that figure to see how the velocity boundary layer grows. All right. Any comments on that one? Yes, sir.
So in every situation, it's going to be like,
Yeah, but this brings up a thing, and it can become turbulent, just like flow over a flat plate, and then things change. So where does it change when we have buoyancy-driven flow? Where does it transition from laminar to turbulent? That previous problem was all laminar. Well, a lot of people have studied it, and they say the transition is when the Rayleigh number, another new number, but the Rayleigh number is just the Grashof times the Prandtl. Sorry, that's just the literature. A lot of people have worked in this area, and that's the best way to represent it. So the Rayleigh is the Grashof times the Prandtl. When that number, the Rayleigh number, critical, is around 10 to the 9th, then you expect a transition. For the previous problem, the Prandtl number is about 1, so the Grashof around 10 to the 9, and the Rayleigh about 10 to the 9, and this is well below the critical, so this stays laminar. But if somebody would have predicted this to be 10 to the 12th or something, then I would have said, whoops, it's going to be turbulent somewhere. Okay, so if you do the Prandtl, what you find is this G beta delta T L cubed divided by nu alpha. The only thing is, the real difference is instead of nu squared, you get nu alpha in the denominator for the Rayleigh number. And again, if the Prandtl number is close to 1, they're about the same value. But this is the transition. So what do you do when you have turbulent flow? Just like we did before. You have to rely on experimental measurements. They did it to a form. They put it into a form for turbulent flow. I don't have time to solve that problem, but I just would point out this last thing I'll cover this table is that you find your geometry, then you take a look at your correlations. A lot of the correlations, some of them are analytically derived, some of them are for experimental. A lot of them, if they have that transition, they become turbulent. There's a different correlation that comes into play. And you can even have horizontal cylinders, spheres, same type of thing. Got to watch your restrictions. With that, I'm going to go ahead and stop for today.